Hello, my dear friends. This is Dr. Mohamed Nezami coming for you from Jerash, Jordan. Um, Welcome again to my YouTube channel. Um, I'm an RF microwave design circuitry consultant. I do stuff from DC to 35 gigahertz. I operate in Jerash, Jordan. That's the ancient Roman town behind me over there. Um, Welcome back. Welcome back. If you just come into your first time watching one of my videos, I have this YouTube channel here, and in it I have all these videos, and I have been doing a series on KA, KU band antenna to LNB structure design, where basically what I'm interested in is illustrating the design of the feed mechanism that goes between the horn antenna and the LNB and the IF signal that goes down to the indoor unit to the demodulator or modem. Okay, so we're gonna finish. If you're watching this for the first time, I would urge you to go back to these various parts. Today I'm doing my sixth part, okay? And basically we're gonna cover the the design of KU band LNB using two orthogonal probes, pin probes. But before we do that, just a little commercial for you. If you have an industrial company that is doing RF products, I would urge you to contact me if you have any design opportunities. I work very reasonable, very low rate, operating outside the US and Europe. I have clients that I could reference you to that are happy in US, Europe, India, Middle East. So you can reach me at this email right here. Okay, or you could find me on my LinkedIn channel right here. So you can scan this with your cell phone, this QR code here, and it will take you to my YouTube channel. Okay. So the other thing that I want to announce is I have a 1 week RF microwave circuits and system design training. Okay, which is that's one. I do this twice a year, and this coming one is in April 22 to April 29th, which is coming up very soon, hopefully. The cost for this course is $2,000 per trainee. I give discounts if there is more than one individual from one organization. The training takes place in Jerash, Jordan here. You get to tour the town and stay a whole week here at my own accommodation. $2,000 includes all your hotel and lunches and so on. And you get to stay in one of the local hotels, such as this one here, which you could look it up. It's a nice place. All right. And basically, what I do here there is I cover all these videos that I did here on the design and modeling of RF and microwave devices and systems. Okay. So you can go back and see these. And in fact, I could customize the course, the training, based on the majority of the people. So I would say that if I get people that are from SATCOM industry, I will shift totally, adapt so the course, the training shop is adaptive so that we could go to any area. All right, so today what we want to cover is basically back to just reminding you, what are we doing? Okay, so basically what I'm doing is I'm trying to find a spot for this picture in here, for this icon, where I don't cover the material. So basically what we're interested in is in design and modeling the feed part that goes between the horn antenna and the LNB or modem, or on whichever you call it. And it varies from large gateways for deep space to sat on the move, tactical, military, to VSAT terminals, and to also KQ band commercial TV broadcast, direct TV. The material that I cover here, even though they're really intended to work for with waveguides, okay, feeding from a horn, we could also, in fact, I will start a series in the future that is for antenna in a package type systems. This is where you have an RFIC that you want to connect to an antenna that is on the same breadboard, okay? And this is a technique basically that is used right now in the flat panel LEO orbit SATCOMs for internet, such as the systems that are coming from the United States, from Amazon and from SpaceX. Okay, so you can see here, I grabbed these from the IEEE journal, and you can see how the RFIC gets connected to an antenna. Okay, this RFIC in here, it could be a single unit cell from an array of antennas, a two-dimensional array, or it could be a single device also. But you can see various formations of waveguide to LNB or LNA transitions. Okay, so basically, if these feed systems, if you look at them in here, they're always using a horn antenna that has a circular aperture. So it interfaces either a circular waveguide or a square waveguide. Okay, so circular waveguide, circle waveguide, circle waveguide. This is a square waveguide in here. I can't zoom in and see this one, but it's probably just like this one here, where the you can see the circular waveguide. So we're dealing with always either a square waveguide or a circle waveguide. And furthermore, the lowest frequency dominating mode in these waveguides is basically for the circle waveguide is the TE11, both vertical and horizontal. And then also the TE01 and TE10 for square waveguide, okay? And I've showed analytically how this one is almost the same as this one with just a small tiny factor, which is basically the cutoff frequency is like 20% more or less between them, okay? You can refer back to my previous videos on this. So what we covered so far is we covered the LNB types, LNB feed types, and these were right here, okay? We have 5 types. We have the first type that was here, which basically what you can see in here is we have the circle waveguide comes in, we pick up one polarization here, and then the waveguide behind, of course, this structure in here behind it, the waveguide transitions to a rectangular waveguide, and then it ends up feeding this here. So you end up picking both vertical and horizontal signals and amplifying them and down converting to an IF. And then the other type, which is the circular waveguide with a septum polarizer. And this septum polarizer is the mechanism in which we are able to separate the two multiplexed. So this is literally a diplexer between the two vertical and horizontal that are coming from a circular polarized signal in circular waveguide. So we've covered this in one of the videos. You can go back to them. We covered this in a video. And then we covered also this. This is where in the same plane you get two orthogonal probes, be it printed like this one here, or be it coaxial, as it is in this case here. We cover this. And then now, so we're left with this type here and this type here. So this type in here is one where the horn, the signal comes in from the horn, propagates down into the circle waveguide and goes to the LNB section in here. Okay, and the LNB picks the signal. It has two probes. This sort of bulb in here and sort of bulb in here. Those are the connections that connect through a pin that goes down along the side of the waveguide and into the 90-degree bend into the waveguide to pick up the horizontal signal, and where this one here goes down in the center of the waveguide and picks up the vertical. And of course, both of them has two-stage amplifiers and image rejection filters and on to the mimic down converter chip. So this one here is what we're covering today, okay? This one here contains both printed and pen tie with a short back end in here, and then those also covered. Okay, so we'll take a look at this one in here, and of course I've got two variations of this, so we're going to look at this. Let me just turn everything on with this. All right, so this is basically what we're going to cover. Here's one of the designs that I want to talk about today, okay? And basically what this is, as we can see, is we've got a BC board in here. This is basically really where the LNB sits. And I've got two transitions from macrostrip to a pin transition that is coaxial in the sense that goes down into the circular waveguide. I've got a dual in here, which is just a metallic pole that acts as a back end reflection for this polarization in here, where the other horizontal one doesn't see this at all. It doesn't affect it and goes back, and it gets picked up by the second probe, which has a 90-degree bend into it. It comes in on the side and connects to this, and then it picks up the signal, okay? And this, of course, you've got this distance in here is a quarter wavelength, and this distance is a quarter wavelength. So it's really a straightforward design. The only thing is you have to really be careful about the design of these transition here. And as you can see in here, I have an opening in the substrate, which is in this case Rogers 4003, okay? And then I've got a bunch of vias around the connection that connects the probe to the board on top, and source to the trace. And this, we call this like, I think they have a name for it. It's basically, this is really implementing a coaxial transmission line on the BC board, okay? Because it's got an outer shield and an inner connector. The outer shield is grounded with a bunch of vias that connects basically the top and bottom. And the bottom of the board basically is as you can see here, it's just basically a ground plane completely. And the whole thing sits on a ground slab, okay? Okay, as you can see here. So let's go through the material. So this is what we're going to cover today. And if you go back to my series videos, we started basically all the way from basic square and circular waveguide until we got to where we are today, okay? And that's usually, we designed first a septum, okay? And then we designed a coaxial to waveguide septums. And then we designed basically a diplexer type to pick up the signal from these both vertical and horizontal. Okay, so let's look at first thing today is let's look at one of these where basically we've got the horn antenna in here. The horn antenna collects the signal from the parabolic dish and then goes down into this circular waveguide in here. And there's a little compartment in here where the LNB board sits in, okay? And this LNB board in here, the IF has an F connector in here, as you can see it right here. That's what connects to your basically indoor, be it modem or be it SATCOM TV receiver. And as you can see here is the board. This is basically what's inside of here once you lift the cover off. And you can see that it's got one probe in here, okay, which sits right in the middle of the waveguide. And that's really what this one is. That's basically that guy right there, okay? We have, well, let me go on the side. Okay. So basically, if you look in here, there's one right here, one probe that goes in right here. And there's another one that comes in that I just showed you. Let's look at the from the bottom view. Okay, so we've got this one in here that comes in with a 90 degree. And there's that one right there. Let me hide this. Okay, now we can see it more clear. So there's one that goes like this to the board, and there's another one which goes, and let me hide this post here. There's another one that is right here, okay? So you can see that these two are basically connecting to the top of the board with the microstrip pickup line, which basically feeds the signal to these low noise amplifiers, okay, both on these. So this one picks up the vertical and this one picks up the horizontal, comes on the side down and bends 90 degree down. And you can see their quadrature. So this one in here, if you draw a straight line to here, to the center, and up to the other pin right here, okay, you can see they're 90 degree apart, that's really what we want to pick up the TE11. Okay, so now inside the feed horn, the way the interface to the feed horn, of course, we got you can see them right here through the one of the LNBs that I have right here also. I happen to have also right here, okay? And you can see that there are two pins in here. Um, let me make this larger so we can see it. Okay, you can see that there are two poles in there, one vertical, one horizontal, and between them there is a dwell that goes from top to bottom, which acts as a short back end to the vertical polarization. So we've got the one in here, that's a horizontal or vertical, either one. It depends where you flip this. And then this is reversed. This is the vertical, and that's the horizontal, okay, because the horizontal has a flexible slit to go in. And this pole in here, this grid pole, I call it in here, acts as a short, a quarter wavelength away from the vertical probe that picks up the signal, where this here is unseen by the horizontal wave that goes in. So the horizontal wave goes in and it doesn't see this pole in here, just goes in and gets picked up by this here. And then in the back of the waveguide, it has a quarter wavelength suction, short-ended, that will basically act as to reflect back any of the signals that propagates that way. Another view of this, just showing you basically the same thing, okay? All right, now pictorially, if you were to draw a schematic corresponding to this, we've got the horn, the corrugated waves in here, and then we've got basically the first probe that goes in, okay? And then at the quarter wavelength away from this in the back, we've got a dual pin that presents a short circuit only to the vertical polarized signal, where and has no effect on the horizontal polarization wave that keeps going and gets picked up by this here, which is basically going into the page, into the screen, okay? And then there is another quarter wavelength suction that is right here shorted. So in essence, now, if you look at this, the impedance loading from this pin from the back short in here is really open, because a quarter wavelength short, as I will show you in a moment, acts as an open circuit, so it doesn't see this. Yet all the signal goes in and gets reflected back, and of course 90 degree one way and 90 degree another way, that's 180 degrees, and gets right in face, sums up with the original wavefront of the wave. Now the same thing happens in here. So the signal comes in here, hits the probe, gets picked up, the vertical horizontal one. If anything passes that, it goes right here and it sees short, dead short, and it bounces back and gets reflected in here. Now, likewise, this short here is at a 90-degree electrical length away from the probe, so it acts as an open. So this one here sees open this way, or sees the impedance of the horn this way, and then sees open this way, okay? And this one in here sees open this way, and also you want really to see just the impedance of this one in here, of the horn, because this one will not get affected for the horizontal probe. It does not interact with this dual pin here, which is, as you can see it right here, from the top to the bottom. And therefore, this one sees, and of course, it doesn't see the other probe, okay? So it sees really the same thing as this one sees. And it's very important that the impedances loading on both probes is the same, because that acts as a basically is what controls the axial ratio, you might want to call it, or the cross polarization pickup. And I will show you in a minute that is in the modeling how that affects us. In fact, let's go right now. So for this one in here, you can see that if you were to look at the frequency response, the S21 on these both of these, so you come in, let's see, no, not this one, let's start with this one here first. Okay, so we got this one here, okay. And so we've got the signal, the feeds comes in through here, both vertical and horizontal. And then I've got another wave I pick up, in this case in here. And what I'm doing, as I will show you in a minute, I'm de-embedding the transmission line in here, because I made this transmission line is much longer than what you really need. You usually pick up the signal and few tenths of mils to few tens of mils, you feed right into the LNA, okay? And so I will show you in a moment that as you can see here, this is the S21, both from the common mode, common signal, or the circular polarized signal to the horizontal. So there's nothing for this wave. And for the vertical is this one. And the difference between them, of course, is in the 20s of dBs. And that's, you want to maximize that. So that's the cross polarization considered in this case. Okay, so let's cover more. Let me maximize the screen in here so we can see this. Okay, so I guess you get the idea of how pictorial this acts like. So let's look at the square wave ones, okay? Even though today I'm only modeling the circular waveguide. So basically, we've got, as you can see, here is the board, which is here with the cover lifted off. And you can see here, this bump in here, this cylindrical in here is really that's the outside housing for this pin here, which goes in and 90-degree bend and picks up the signal for the horizontal portion. Okay, here's another variation of this. Basically, it's exactly the same thing. For the circular one, I went through this a moment ago, so just to repeat that again. So we've got one vertical pin in here that goes down to the waveguide, and then we've got two stages of LNA misfit devices. And I've got a hairpin filter, and then which acts as an image rejection filter, and then we go into the mimic down convergent chip, and then of course we go into the IF signal, which goes right here. This here is basically for DC protection. This is a Xeno die that clips the signal, the DC signal that comes in from the indoor unit. So the same thing on the side in here, you got this pin here that goes down and bends 90-degree bends to line up with this and picks up the horizontal one, and then goes through two stages of amplification as well, with the filter in here, and then into the low noise block down converter chip in here. This here contains the phase lock loop and the IF amplification stages, the mixer, and like for instance, this is the crystal in here, 25 megahertz crystal, which acts as a reference for the phase lock loop that is in here. In some cases, you get the references that is not internal generated, it comes in from downstairs from the modem, where it's disciplined via GPS or organized crystal. All right, so here, so how we model this is basically we started modeling in one of the previous parts where we took a circular waveguide and we inserted orthogonal pins that you can see in here through from the horn view point of view. And then we just pick up the signal. We just adjust the lengths in here. We run the optimizer to adjust the distances and the length of the probes. And that's all we do. So, and that's shown here also another variation of these that I grabbed off from the internet, basically. So we've got one pin right here that goes into this amplifier, another pin right here that goes into this amplifier. Both of them go into this T-junction combiner and then into another amplification stages, and then into a hairpin filter, and then goes into the mixer and down further. So this is really utilizing a discrete mixer, not an integrated chip like this one here. Okay. All right. So what I'm going to do in today's session, I'm just going to add a BC board to this. This one was designed previously. You can go back to my other video where I talked more about this design here. So this is the bottom of the board. So we've got the board in here, okay, the LNB board. And then what you can see in here is this here. One is a vertical horizontal pin, and one is the 90 degree. And the waveguide basically comes on this way. It comes this way. So this goes into it vertically, and this goes horizontally. And you end up picking both of these signals like it is in this one here and in this one here, and you amplify and then all the way until you combine and you go to the IF. Another view of these that I will show you in a moment also, so you can see in the bottom both the probes, okay, and this uses this mimic chip. Another closer look at this type here, which uses a circular one. In this case in here, and what you can see here, they put the reference oscillator, reference crystal down beneath the board. That's okay. So this is basically what are the probes that goes into the waveguide. Same thing for this guy, very much the same. So we've got one pin here, one pin in here, two stages of amplification, two stages of a hairpin, and then onto this one here. Okay, the same thing that goes in here, okay? Very much the same, so. All right, so let's put some principles quickly. So we remember that the cutoff frequency for the circle waveguide is this one here. That's the coefficient from the Bessel function, the lowest order Bessel function, which corresponds to TE11, the lowest frequency dominant mode. And then for the square waveguide, of course, it's really is this value here, okay? So, and this is TE10. As you can see, it's A and there is no B, all right? And of course, in our case, A and B are equal because it's where waveguide. And then we're using a microstrip line where the characteristic impedance of the line is dependent on the height to width, and with this here, this coefficient in here. Of course, we got the pins, both these pins are basically modeled as coaxial lines, the way they go through a board, okay? And that's what I did in here, basically. If you look at the this guy in here, that's a transmission line, basically. This is it. In here, you can see the purple in here is basically the insulator, okay? And this is the interconnector goes in here. So what I did is now depending on how you want to do this, you want to do it and inside between the inner and the outer, you use an insulator or you don't use an insulator. And that's why I have two designs. I have one called air and one called Teflon. So basically in this one in here, I did not use an insulator. And so you end up with a lower loss line because basically it's a coaxial line with the insulator. There is no insulation material in there, so there is no dielectric loss. So you pick up few tenths of a dB on insertion loss on this one better. And so I'm going to show you that in a minute when we get to this. So if you look at the probe itself, that's how we design it, depending on this. So the outer to the inner diameters, and with this coefficient in here with the insulator, so the impedance in here is divided by square root of the permittivity of the insulator. So if it's air, this is basically is 1. Okay. All right, and the cutoff frequency is given by this. Okay. All right, so where do we put the probe? I went through this in the previous videos. So basically, if you look at the propagation of the E field and the magnetic field in the TE10 mode, you can see that the wave, basically, the amplitude of the E field and the H field is really proportional to a sine wave signal. And that is basically, it goes in like this, and then goes up and goes again like this. So you get places where you can put the probe anywhere you want, as long as if you put short in here, you really want to be further away from here, quarter wavelength, which corresponds to the right at the maximum field intensity point. So we want to be at the middle of the waveguide and a quarter wavelength away alongside the propagation path. Okay. And you can see that from the current density as well in here. All right. So pictorially, and I went through this more times. So basically what we want the quarter wavelength short in here from the probe. Okay. And the same thing, this is short. So quarter wavelength from this probe, the vertical probe and the horizontal probe. And if you look at the transmission line impedance, input impedance of a quarter wavelength line, you substitute the length in here as quarter wave, you end up with this equation here, which basically is that the input impedance of a quarter wavelength waveguide section is basically the characteristic impedance squared divided by Z load. And in this case, Z load is 0. So that means the Zn is actually infinity. And of course, now in the optimizer, when I run this in the HFSS in here, really the back end, the short back end. Okay, this one is missing some parts. This we will put this back, show you, put back the other stuff. Okay, so basically, so basically that's what the okay, the quarter wavelength line distance or distance from the horizontal probe in here, this one, we put it initially you start out putting it at a quarter wavelength. So we can see here the back, the way the back short distance, in this case, I put it as a quarter wavelength away from. And you will see in a minute that it's not exactly where the resonates at where the frequency that I wanted. In this case, this one here, I ran it for FC, let's see, F is 11.5 gigahertz. So, and that is because it's really ideally, it's loaded, more stuff loading parasitics in there because of these things. So what you want to do is you end up with, what I end up with is basically going into these coefficients in here, and let's see, we go into these guys in here, and I come into the back short distance in here that I showed here. And so you basically make this tunable, make it tunable, and you sweep basically. Oh, this one is variable right now. But you put this sweep, and you sweep it either by hand, tweak it, and get the feeling where it should be, or you can run the optimizer on this. You can go in here and add an optimizer, and that's what I did to get to some of the for the final designs. Okay, and you'll see that in a minute. All right, so that's a little theoretical background. So let's get to the first one. Okay, so I'm going to talk about these slides are going to be presented in the you can get them, download them from LinkedIn. So I have them at LinkedIn. So let's start with the first one where the insulated probes, the probes have an insulator from the outer, so there is Teflon basically in here. This is for the vertical and horizontal. So this is basic structure, and I go through. This is the board on top. I stitched some vias in here so that I get more isolation. And it turns out this is really very critical. And you can see that from the layout of these. You can see that the compartments, you see these compartments? They are so critical. Even the vias, let me go through to go back to the board. So you see these vias in here? They're so critical. Okay, right now I don't have them uniformly around the circle, but they're sufficient. But these are critical to the isolation between this probe and this probe. Okay, and the signal leaks, and there are more. As you can see, let me see. These ones, there's more vias in here that I had to stitch to get to this, and that's why you see this on the basically on the layout. Whoever did this layout, as you can see, they basically made sure that these probes are surrounded by stitching vias so that the signal doesn't leak to the other side. Because you can see this probe and this probe can easily get surface propagating signal that crosses between them, and that distorts the signal. So if you have, and in fact, that's one of the system level studies that you would do is you would create a model of this and pass it on to the modem designer, tell him this is what I have as my isolation transfer function between the vertical and horizontal, see what impact you can get. Okay, so it's very, very critical, the layout of this, and that's why HFSS is beautiful for assuring. I almost spent so much time doing this detail in here to get this to work than I did to do designing the whole thing from the ground up. Okay, and so all right, so let's go and just look at this. As you can see it sideways, how it looks like. This is how it looks like metallic work. And this one in the side in here is the one that picks up the signal. That's what you see on here. Let me show you. That's basically, let's see one that shows it. This one. Okay. Okay, here we go. Okay, here it is. That's this guy here. You can see it. In my case now, I did not draw it exactly completely off the so you can see there's a little gap in there between the body of the let me let me as you can see, oh, let me do this. Let's see, aluminum, select all, and let's go a little like this. Okay, so you can see that the that's what the side in here. So why this is okay. Let me go this way. So we gotta go like this to see it. Okay, so you can see that I'm not seeing it like this. Interesting. So let me take it and completely make it zero transparency. Okay. All right. You can see that I have a little gap in there. Can you see it right there? Now, of course, that's just for me to simulate the electrical, but in actuality, you can't really do that with a CNC machine or even aluminum die casting. So you would want this completely to be solid with the body of the circular waveguide. Okay. Let's see. Let me just make this more clear, transparent so we can see the other stuff in there. Okay, so let's go through this and basically let's get back here. Okay, so got this. This view here, basically, you can see what this one in here is this one in here, okay? And you can see this one in here is that one right there, okay? And of course, the other thing that I want to warn you about is really the hole that you can see there, this hole in here, this clearance here is really is part of the characteristic impedance of the transition between the BC board to the actual coaxial line section in here, which is the probe in this case, or the probe feed. Well, the probe is considered this piece here only that really enters the vacuum of the waveguide. But this here is part of this is considered as a coaxial line feed in here. So, but there's another coaxial that is printed, which is basically this one here. You got to get the signal from a microstrip to a coaxial BC board, printed coaxial, and then to an actual coaxial. So you've got three transitions right there that you really gotta make sure that it works well. So I ran this, and of course, this is the first thing we want to look at is the return loss. This is the return loss on the basically for the vertical and horizontal. And you can see they're not tuned at the same frequency. And that's what I meant by saying that due to all of the loadings that you have to deal with in here, you really gotta just run the optimizer to get these lined up, okay? So it becomes tricky. And this is basically the insertion loss and the isolation. You can see because the transmission for the vertical and horizontal from the vertical and horizontal at the input, meaning what I do here, this is sweeping. I sweep basically from the common port, okay, to the vertical and to the horizontal at both modes because I'm running 5 modes. So what I do, if you go here, there's 5 modes that I'm running. I'm just interested in the first 2 that are these guys right there. You can see. Let me go back. Okay, so I'm interested only in these 2 in here to see how they propagate to this point and to this point. And that's what you see in here, basically. And you can see the insertion loss is 0.5 dB, okay, which is good. I mean, we're assuming that we're going to get an LNA of about 0.5 dB and 0.5 dB here. That's a dB of overall noise figure for the LNB, okay? And then, of course, I'm running this is the vertical and horizontal, the macro strip, okay? Run this for the modes. I'm just trying to make sure here that I'm operating between 2 modes, the lowest mode and the highest mode, and I'm operating in here so that I don't excite higher order modes. The impedance looking in, you can see that it's 50 ohm, and of course the waveguide is 750 ohm. Okay, so that really, what we can see next is let's see some movies. Let's see how the E field propagates into this. And it's going to take a little bit. So let's do something else. Let's look at it here until we get so they got this one in here until it solves. This is the result I got. So we got this here, return loss. This one we got. And then we got the E field. And you can see the E field. I'll show you in a minute live where this is. As you can see the horizontal signal being picked up by this probe and the vertical one picked up by this probe. And on top, you can see in the substrate that you're getting really a little bit of leakage between the 2 channels, okay? And this is just a view from the bottom. It's showing how the signal is propagating into the board, going up to the board. Okay, so here's one polarization, here's another polarization. You can see the nice thing about this, you can see that this here, ideally, it has to be the middle of this pattern here, because this pattern here repeats every half wavelength. So middle of that is really where you want to be, because this is a short end in here. From the short end, it has to be a quarter wavelength, okay? And so that's why this is running at 11 and a half gigahertz. So that when you look at this, you can see why the system is not, it's not tuned to 11.5. It's more like 12.5. It's because really there has to be a little adjustment on the location of this probe. But I said to myself, that's enough. So okay, so here it is. We've got this is going. Okay, why is it not running? Okay, so because I'm not animating. So hold on, let me turn this off and let's just look at this one in here. And I'm gonna animate this so we can see it. All right. Okay, let's see some stuff until we'll get this one. So the next section, I'm doing this with an air-filled probe, which means the vacuum in here is air. And a lot of these LNBs that I've looked at, you can see that here is the insulator. You can see that they are really doing a small section of insulator. So this is a true coaxial one. This one, it must have fell off. The guy, he must have dropped it while he was pulling this away from the structure, the assembly. Okay, so the other one for the airfield, basically, you can see that this is right on frequency. Oh, this is almost half. Okay, and you can see the pattern from underneath. And this is the so you can see 0.10 of a dB instead of 0.5 dB. So you can get much lower loss than you would get. Of course, shift back to 11 and a half, as you can see here. This is closer. So the insulator does shift the frequency a little bit. So let's go back. Must be still running. Okay, it's trying to solve. So let me talk about something else until it's done. So basically, with this, I have covered all of these 5 types in this series of 7 videos up to now. The only thing is left is this type in here. And this type is interesting. I'm excited to see how it works. Because this one in here, this has a benefit over this, is that you can see that there is really no distance between it's thinner than this, because in this one in here, you need to be spaced between the horizontal and the vertical. In the middle here, there's that pin, that the back reflection pin, which is inserted. You can see that meaning this pin in here, this dwell here, it's you don't need it, and it's printed. And so the way this works, and let's zoom in on it here. So one of the probes is printed. So go in here, you amplify, and then you go further into the down converter. And then there is this piece in here, which behind, it has a ground post. This is plated, ground plated. You can see the ground stitching, the V is in here and V is in here. And this is also grounded, this from the back. So this acts as a back end reflection for this probe in here. See this solar bulb in here? That's a pin, metal pin that goes in and has a 90-degree bend to pick up the horizontal. So this picks up the vertical, okay? And then this vertical in here, the back end short is the cover, the lid on this. So the lid comes in here and covers this, and the distance between the ceiling of the lid and this printed pin is a quarter wavelength. But for the second one, we've got this one in here. Remember, the wave is propagating from that side coming in here. And in this one, it got 90 degree, and the back short for this pin here is really what's between, it's this here, because it has a printed, it's printed pattern on this side in here. You can see that on the next part. So what I'm going to do next is model this and show you how this one works. So hopefully, let's see if this one is. So this is still running. So let me uh, see what's going on here. So okay, so basically, let's see. We got this running. So let me try to get this picture as large as possible so we can view this. Okay, so basically what we have right now is we have a counterclockwise signal going, okay? And you can see that of course, you can see the propagation is going counterclockwise. You can see the signal is going in. And the first thing is, of course, we got the one on the side here is what's picking the horizontal wave, okay? And the other one is this vertical in here that's picking the vertical wave. So we can view this from various sides. So let's see this here. So let's fit it all. And you can see that the signal comes in, propagates, and then goes in. And this right here is the metal dual. This is the back end short for the vertical polarization, okay? Where this one here is the back end of the waveguide for the horizontal. So if you look this way from the bottom, you can see the waves are going in. Basically, this is what's picking the horizontal, and that's if you let's see, that's the pin. No, the horizontal pin is let's see, this is copper, so we got line one. No, that's horizontal, and the what is it? Oh, okay. Let me just make sure I have everything is on. So got a lot of vias in here. Okay, so okay, I see what's happening. So let me just try to pick up the just can't see it from the okay. So let's look at it from the back. Okay, you can see the this one here and the other polarization. Left side, we saw that one. Okay, and let's go to the top, of course. And as you can see now, this is the injection point. This is where we inject the signal. And that's basically the common part right there. So you can see the signal is coming in here. And then, of course, you can see that it is basically the first thing is going in and gets picked up by the vertical one in here. And here's the propagation into the microstrip line. This is the synthetic or simulated, BCB simulated coaxial transition, okay? And you can see that the other side, okay, okay, this is the metal back in short for this guy here, for the vertical. And this is for the horizontal signal is being picked from the side, off the side, as you can see, 90-degree bend through a 90-degree bend is going into here, okay? And so that's why when you look at these things, there is no way to match the SNR between the two various polarizations, because really it's naturally that this feed here is longer than that feed. This one is basically just runs straight down, where this one has to run straight down, has a 90-degree bend, and then it goes through an additional section to go through the waveguide, outer metal into the waveguide. So you can see that. Okay. So now that's this. Of course, this is running counterclockwise right now. I could run it for the other polarization, just change basically a 90-degree minus 90-degree. Okay, ladies and gentlemen, I will post more of these videos. I'll post separate videos emulating this, but I'm just going to cut it right now at this point. Okay, so that's it, ladies and gentlemen. So back to our thing in here. So basically, again, this is Dr. Mohamed Nezami coming for you from Jerash, Jordan, and we're still continuing the series. And I will, for the slides in here that you see here, you can get those slides from my LinkedIn account. Okay, you can go in there and search for them. They'll be there. I'll try to even put them in the comment down there or in the more notes on the video. Okay, ladies and gentlemen, so I would like to, this is Dr. Mohamed Nizami again from Jerash, Jordan. Thanking you again for tuning in, and I'll see you in the next and last section on this series, which is next week, that I'm going to look at this type here. So we still got this type, which is a mixture. It's an interesting one because it mixes the printed and the metal pin probe both together. So we'll look at that one. Okay. So what we talked about today was interesting, and I hope you enjoy this. There's still more work to do on this here. There's more optimization I could do, but for right now, I'm just going to stop it. I illustrated the principle of this, how it works, and I'm very satisfied. Okay, so the like in this case, this one was for the air-filled one. Um, this one was okay. The isolation was about 19 dB. I noticed that there's a little trade-off between the insertion loss and the insertion loss for the air-filled one and the isolation, okay? And so you might think, you might try to think why that is. If you have any ideas on this, please leave me a note. Okay, well, I do thank you very much again and have a great day, weekend, night, whatever time it is on your end. Appreciate it. Thank you very much. Have a great day.